Okay, thanks for the introduction. So some of you who know my research group know that we've been working on these snake-like robots for quite a long time. And what's great about these devices is that they can thread through tightly packed volumes, get to locations people and machinery otherwise can't access, and they're capable of producing kinds of locomotion that machines of their size scale normally can't. So a common question that we get when we're working on these robots is, are these biologically inspired? And I think my computer just crashed. PowerPoint. Does anyone know what to do when PowerPoint freezes? I wish the clock would stop. Yeah, do it. Just try hit buttons. Okay, so the thing is, a lot of times people, what they do is they ask us, is this biologically inspired? Because if you look at a real snake, you look at the robot, there's the obvious similarities. But the truth is, we, in our experience, we went and started to develop all sorts of core principles, and then from that, we're able to make the robot go, but we were only able to make the robot go so far. So what I want to do today is sort of change your view a little bit on what is biological. Oh, let's do that. Yeah, you did hit the wrong button. All right, let's let it go. It'll work its way out. So what I'm going to try and do is do the challenge of giving a talk that has really great videos without the videos and see how well that works. So the thing we want to do is we want to sort of change our view of what we mean by biologically inspired robots. So instead of just looking at the biology and saying, yeah, that looks nice, and try and copy it over, what we want to do now is try to understand what are the core principles that biology is trying to demonstrate. Can we identify those principles and then replicate them on the robot? But I think we can do a little bit more. We can sort of use the robot as a template that biologists can otherwise... Oh, that was the thing I was looking. Let's close the program. Cancel. If anyone's been in this situation before with PowerPoint, now's a good time to come up and help me out, because I don't know what else to do. That's great. That's perfect. Ladies and gentlemen, Chow Wei Gong, with a backup to my talk. The irony is you clap more for Chow Wei than for me there. Why don't you go on this slide here? Okay. Why don't you advance it for me?
Okay.
'Cause it's a Mac, and I don't know how to use a Mac. Okay, here's the slide. This is the second slide. So, go next slide. So what we want to do now is we want to ask ourselves, what are the principles that biology is demonstrating, and then can we replicate those principles to make the robot better? But perhaps we can return the favor to biology by saying, hey, here's a way that you can test some of your ideas on a template, our robot, and then see if those ideas corroborate what your theories were in biology. So what we're trying to do here is sort of a bidirectional illumination where it's bio-inspired robotics as well as robot-inspired biology. We want to kind of go both ways. So let's talk about principles. Here, what I'm going to do is I'm going to point out some of the people that have influenced my group's thinking. This is not meant to be an exhaustive survey of what's happened in the field. However, if we're going to talk about snake robots for a second, we can't not mention Professor Hirose and his pioneering work from 1971. And what he gave us is not only building the first snake robot, but he prescribed this curve called a serpenoid curve that describes, sort of in terms of curvatures, how a wave-like mechanism should locomote in the ground. This is a very technically challenging talk. So good night. So the next person that influenced our thinking that's not our fault. The irony is my computer did come back. We're going to run PowerPoint. Okay, that's good. So the next key influencer was Greg Chirichian. And what he did is he built the first snake-like robot in the United States, where he coined the term hyper-redundant manipulator. And one of his ideas was this notion of being able to fit a mechanism to a curve, thereby reducing the computational burden on inverse kinematics. Instead of one large inverse kinematics problem, you have a whole bunch of small ones where you fit to a curve. And he also started thinking about representing these curves in terms of modes. And that's another idea that helped us quite a bit. Next slide. Finally, next is I want to acknowledge Jim Ostrowski. He was a graduate student when I was a PhD student as well, and he introduced us to these notions of geometric mechanics, which allowed us to rigorously begin to understand what it means for a system to locomote. And finally, Mark Yim, he's helped us in a bunch of ways. One of them is he gave us his initial designs for his modular robots. So ideas in modularity helped us quite a bit. But also, because of the specific design that he gave us, it got us thinking about multiple waves that may be passing through this snake robot. Of course, we have to acknowledge Joel Burdick. He was Greg's and my advisor, and it was his intellectual leadership as well as taking what would seem like disparate problems and helping us put them together to address these problems. And then finally, we have to thank the snake. This snake also did provide us inspiration. And here I want to point out my biological collaborator and a physicist, Dan Goldman. He was the one who really got us thinking about having to specifically look at principles in biology and then seeing what we can do to replicate them on the robot. So let's start talking about some of these principles. I think we're all familiar with this term, a gait. A horse gallops, we walk, run. These are different gaits. These are cyclic motions in our internal joints, our internal shape space, that allow us to propel forward, say, in our position space. Now, horses aren't the only animals capable of gait motion. These worms, snakes, hyper-redundant mechanisms, they're also capable of gait-like motion. And here, I just noticed a problem with your talk. All the videos aren't linked. Here, what you would see with another, I bet you weren't going to see this many changes of talks in one. Hold the microphone. You all applauded maybe a little prematurely. So this is a lesson to students out there. Always check your talk before the presentation. Where's the clicker? Yes. Okay. So hyper-redundant mechanisms in biology also are capable of this kind of gait-like locomotion. Here we have an inchworm, sidewinder, and so forth. So what I want to do is take a deeper look as to what's going on in this gait-like motion where we're separating our shape space from our position spaces. This is an equation called the reconstruction equation that I learned from Jim's thesis topic, where essentially we have our instantaneous velocity, our xy theta dot, let's say in the plane, multiplied through a linear function through our shape variables. So this is like a joint 1 theta dot, joint 2 theta dot, and so forth. If you blur your eyes a little bit, it looks like a Jacobian, and followed by a momentum term. Now, my grad student, Eli Shamas, he was able to use this equation to analyze a variety of systems which at the extreme are kinematic systems, but in the middle have some dynamic components. However, this analysis really took off well when Ross Hatton came over, and he started just looking at the kinematic systems. And one of the things that's great about Ross's work is that he was able to show, just by simply modeling kinematic systems, how much representation, how much analysis you can get away with in terms of making the snake robot go, as well as modeling the biology. So what Ross did is, if you look at this equation again, our body velocity times this Jacobian term and our shape velocity, what you can do is if you plot the rows of this matrix here, remember Jacobian, the columns tell you the contributions of joint I, the rows tell you the contribution in the workspace direction you're going to go. So let's say the first row here would correspond to, say, your x dot velocity. What he was able to do is you plot a vector field, one for each row of this matrix, and then in this vector field you can draw a loop that corresponds to your gait, where the tangent, if it flows with the vector field, you're going to have motion in that direction. If you're perpendicular to the field, you'll have no motion because the dot product of two vectors is 0. Now, designing gates in this way can be a little bit cumbersome, so what we were able to do next is, again, here's our equation. If we integrate our velocities, integrate this side, we'll get some form of displacement. And instead of designing gates in this vector field space, we can take recourse to Stokes' theorem, where instead of integrating along a path in a vector field, we look at the volume contained by that path. And then in the right coordinate system, we're actually able to show that this approximates true displacement. So now, designing gates for these simple, say, 3-link systems is relatively straightforward. All you have to do is look at one of these functions, draw a loop that encompasses the volume, and the volume enclosed is how far you're going to displace. The thing is, this is a little bit of a naive system. For one thing, this is a 3-link robot. The snake robot in which we're interested has 16 degrees of freedom. So what we're going to do is we're going to borrow some ideas from RSJ and from Greg. And instead of thinking of these things in terms of joint angles, let's think of them in terms of curvature modes. So an example of a curvature mode when you have joint angles is this nice Dirac delta function. It spikes at joint 1, spikes at joint 2. But instead what we'll do is we'll have our curvature modes be sinusoids. This is exactly what RSJ's serpenoid curve was. He was able to show that you had 2 sinusoids, or he intuited 2 sinusoids was enough to specify what that wave equation was like. So now what we're able to do is prescribe a path using the same gate design tools, looking at this height function space for this continuous robot. The thing is, the kinds of motions that the snake robots and all these mechanisms are capable of doing, they work in 3 dimensions. And everything here I just told you was 2 dimensions. So what we realized, and again, this is some inspiration from Mark, is that there's really 2 waves that are going through the robot or through the mechanism or the biological mechanism at the same time. One is a horizontal wave or a lateral one, and the other is a dorsal or a vertical wave. Both waves provide locomotive benefit to the robots, but the vertical wave is a little bit different. What it's doing is it's brokering contact between the environment and the mechanism, almost like a legged locomotion system. So with that in mind, we were able to come up with what we call a generalized serpenoid curve, which is essentially a serpenoid curve just going through the horizontal wave and the vertical wave at the same time. And these are the parameters that describe that space, and 7 or 8 parameters. And with that, we were able to model a lot of biological behavior as well as make the robots repeat that. However, we found all these just through brute force searching our 7, 8-dimensional spaces. I have a lot of undergrads working in my group, and that's what they were doing. So we want to come up with a more principled way of finding these parameters. So let's just use sidewinding as an example. So when a snake is sidewinding, it's sort of moving like a tank tread. It's taking part of its body up and putting it down in front, and so forth. It's repeating that process over and over again. So we had, Ross and my students, we had this intuition that it was like a cylinder with a moving tank tread. So what we do is we wrap a backbone curve around that tank tread so we can sort of visualize it. And then we can animate this backbone curve to get what the joint trajectories are to achieve this motion. We perform a Fourier transform on these joint trajectories, and now that we're living in the trajectory space. And you see very quickly, we get an equation where there's just one mode. Only one mode really dominates this motion. It's interesting to note, by the way, that even if we vary the eccentricity of the ellipse a little bit, it's the same frequency, it's the same mode. And it's also interesting to note that the phase offset, that's that delta there between the vertical and the horizontal modes, is pi over 2, and that was something that was corroborated by the biologists a long time ago. So we were able to at least confirm what the biologists were able to see. Thing is, we want to have something a little more interesting. Snakes can turn. So what we did here is we developed this gate. Chao Wei, my assistant, he iterated on Ross's work, and we developed this gate called conical sidewinding, where instead of rolling like a cylinder, we roll like a cone. And again, we fit the, another picture. And we fit the backbone curve onto this cone. The aperture angle of this cone determines the angular velocity or your steering direction. So what we were able to do now is do a Fourier transform on each for each possible aperture angle, and that's what we're plotting here. This vertical axis is now aperture angle, and what emerges is that three dominant modes, except for the one in the middle, because that's where you're going straight, emerge as to what would be the driving factors for these conical sidewinders. However, with some inspection, what we were able to do was observe that there's this linear function multiplied by one mode that gets us this conical sidewinder. So what's nice is now we have a single variable, this a of n, which we can vary in order to steer the snake robot and still have one mode to provide locomotive force. The thing is, one, we had to use our intuition to come up with this linear function, and two, we want to let ourselves discover other kinds of motions other than this conical sidewinding. So once again, we return to the snake for some advice. So here, this is data that we collected from Dan Goldman's group, and what we do is for every gate, every possible gate, we plot, again, the intrajectory space, what the motion is, and then this color choice is a little bit off here. This is gate 1, gate 2, and gate 3, and you'll see why the color choice is off in a second. But the thing is, we can't do a Fourier transformation, we can't do a singular value decomposition on this entire space because this is too much data. But what we did instead is we do a Fourier transformation on each slice, or we decide what number of modes we want, and we just project our trajectory data onto the basis functions of the Fourier transformation for each slice, and that leaves us with a variable in the vertical direction, the behavior or gate direction. And there, we can't use Fourier analysis. Again, it's too much data, and the other thing is it's not sinusoidal the way you'd expect. But what we were able to do instead was factor out this problem and do an SVD on this vertical axis. And what we're able to do very, very quickly is from the data we were able to collect, we were able to observe that two modal functions dominate. And with those two modal functions, we were able to derive a controller that very easily allowed us to achieve a wide variety of motions that, again, were corroborated on the real snake. So here's the controller that was automatically found out, and we were able to verify what those modes were on the real robot. Now, with these modes identified, we were able to now search this lower dimensional space to come up with motions that were otherwise, hard to reach through our derivation. So here we have this snake robot. This is real time, turning wickedly fast using controllers that we derive from the real snake. The thing that I'm going to run out of time for, which is unfortunate because this is where it gets interesting, is we have to go back and look at the vertical wave. Because right now, all we've done is we've analyzed the horizontal wave, and then for the vertical wave, we put the same wave through, but just added that pi/2 offset. What we want to do now is intentionally respect what that vertical wave is. The thing is, we don't have data on that vertical dimension. All the data we get is from above. You can't aim the camera from the side. However, we were able to observe that when the snake does make a point contact with the ground, its velocity instantaneously is 0. So looking for those 0 velocity points, we were able to quite faithfully represent where the snake is making contact, and we just pass a sinusoid through those points of contact to approximate what our vertical wave is. And in doing that, we were able to run through the same factorization algorithm again to come up with really cool turning gates that sort of work in, say, sand. But this is the thing that we're really happy about. What we have here is a cool turning in place gate. What's happening is when a real snake turns in place, you'd figure that its wave is going from head to tail, so it's going along like so. And when it turns around, makes a sharp turn going backwards, the snake does not reverse the direction of the wave. Okay, the waves are still going forward. Now, for us to start walking backwards, we just change the direction of our internal joints, and back we go. For the robot, it's also easy to turn the joints, the directions of the joints backwards, but the real snake doesn't do that. What happens, and we were able to observe this because of the analysis that Chadway found, is that the real snake, its vertical wave, experiences an instantaneous phase change of 180 degrees. And just because of that, with the gates, with the wave still going forward, we were able to make the snake, we were able to explain why the snake reverses and how to make the real snake robot go in reverse. So I only have 4 seconds left, so I'll have to end it there. But the take-home message that I really wanted to say is, if we were to copy biology, let's look at the principles, try to copy the principles, and then let's return the favor to biologists by saying, hey, our robots are good test platforms on which you can validate principles that you've taught. And this collaboration with Dan Goldman's group at Georgia Tech has been incredibly fruitful for us. And already I'm proud to say we have our first paper in science coming out. All right, with that, I'll stop. Thank you.
A set of differential equations. At the base and the tip, there are complementary boundary conditions, and by solving this boundary value problem, we can obtain the shape and configuration of the robot. Now, the compliance follows directly from the forward kinematics model, and it represents a linearization with respect to the tip applied wrench. Also here, we have a complementary set of boundary values at the 2 sides of the robot. And by solving this boundary value problem, we are able to find the compliance of the robot. The solutions can then be assembled in form of a compliance matrix. An important aspect of our study is the experimental validation. Here we took a flexible tube, attached it to a 6 degrees of freedom force sensor, and applied arbitrary loads to the tip. Now, only from these force measurements, it's possible to obtain the tip position, tip forces, and compliance of the robot. We also used a 5 degrees of freedom position measurement in order to obtain the tip position. Compliance, however, cannot be measured directly. Instead, we can evaluate the tip velocity resulting from the compliance matrix and the change of external forces in time. And we can compare this to the differentiated position measurements. Now, coincidence between these 2 curves proves as the validity and correctness of the compliance matrix. Here, on this graph, you can see these velocities for some arbitrary applied loads. The compliance matrix on its turn can then be used for either force control to assess behavioral properties of robots or other aspects. Here on this video, you can actually see a force control experiment where a rigid robot and a flexible instrument is attached to the robot. So the compliance matrix here is used directly to cancel out the stiffness of the actual device. Thank you.
For the proposed University of Tulsa hand, an under-actuated hand with 2 synergies, each controlled by 1 of 2 extrinsic actuators, capable of achieving a wider variety of useful postures in single synergy hands, and where the force and displacement from the actuators are transmitted through an elastic element or compliant web to the system of finger tendons that are biologically inspired. We base this on the idea of postural synergies, which are the coordinated motions of finger joints, and the combinations of these motion patterns comprise the grasp posture. We drew some inspiration on some previously existing under-actuation strategies. For example, the Toronto Bloorview-McMillan hand here, which has a branched interconnection where each finger is connected to a single actuator in the palm. And an alternative under-actuation strategy, the University of Pisa hands, which features a cable circuit interconnection. But while both of these hands have only a single mode of conforming to an object, we propose a 2-synergy system with the elastic transmission element. And our paper proposes that we model the complex elastic behavior of each constituent element as a multi-port network, and a concept borrowed from electrical engineering where each complicated system is treated as a black box where we only consider the input and output behavior. And we also develop expressions for the interconnection of these elements. So in this paper, we derive a general expression for multi-port networks connected in parallel and in series. And the positive definiteness of the stiffness matrix is proven to be positive definite, which indicates that the graphs will be stable. We also analyze or apply this multi-port network analysis to a 3-digit planar mechanism. And in the future work, we're hoping to develop a toolbox of compliant mechanisms with unique characteristics to build up this compliant web and also experimentally validate the 2-port network modeling. So if you're interested in the details about the theory and its implications, then stop by the interactive session. Thank you.
Hi, today I'll be going through how the fastest robotic fish was developed, our robotic fish, namely iSplash2. It's able to actuate at high frequencies of 20 Hertz. This is a real-time video that shows the video's not working. Here we go. This real-time video shows the bolt actuating in air around half its maximum frequency. The prototype is able to transmit large forces with accurate kinematic parameters. This real-time video shows the first ever run. iSplash2 is capable of outperforming the maximum velocity of real crangiform fish, measured in body lengths a second, achieving a consistent swimming speed of 11.6 body lengths a second. In comparison, current robotic fish have achieved a maximum velocity of around 1 body length a second. Live crangiform fish, such as the common carp, cruise around 3 body lengths a second and have a maximum velocity of 10 body lengths a second. Our main objective was to develop a high-speed build to achieve the fastest swimming speeds of live fish so that navigation for a real marine environment is possible. The traditional approach of previous designs typically confines the waveform to the posterior half of the body length. This approach creates anterior destabilization for free-swimming robotic fish, therefore leading to kinematic errors over the full body length. Based on intensive observations of real fish, we introduced a full body length approach on our first generation prototype, which was found to coordinate the anterior mid-body and posterior parameters, increasing linear swimming speeds. iSplash2 weighs 0.8 kilograms and is formed in PLA filament. The prototype has a length of 32 centimeters and has a high power density with the primary actuator 75% of the total mass, distributing power across the full body length. We found that developing build has a force of up to 9 newtons. We can see the system is robust and consistent, attaining high tail frequencies without early peak decline or mechanical failure. Therefore, we look to continue to raise frequency to achieve even greater speeds. This real-time video shows the latest version, able to accelerate to top speed in approximately 0.6 seconds, and carries its own power supply, which lasts for around 10 minutes at maximum velocity, far surpassing real fish, which have a limited duration of only 1 second at top speed. Thank you.
Hello, my name is Hee-Jun Kim from Chungnam National University, South Korea. And now I'm going to talk about designing a multifunctional leg inspired by diving beetles. The performance of the leg has been verified through the underwater experiments, and you will see today assembled a multi-legged underwater robot. Let me start with the motivation of this work. There are many type of underwater robots using different kind of proposals. While they are mostly operated for ocean detection, we approach this matter for the purpose shown in the conceptual drawing on the right side of the slide. The robot started to be developed for working and swimming underwater, and to efficiently overcome environmental limits such as high tidal currents and then poor visibility and also uneven seabed. Currently, we have focused on establishing swimming technology for this, and for this region, a diving beetle was chosen for the research. Off the record, somebody asked me why the diving beetle was chosen. Then I all the time say that off the record that the diving beetle was cheap and easy to get raised. And here is the overall process of our work. The research has been divided into two areas, started from locomotion and structural analysis of the diving beetles. Firstly, following the green line on the above, a swimming pattern generator has been designed to produce biomimicking locomotion. Simultaneously, the multifunctional leg has been developed by employing the structural advantages such as bristles and passive segments on the diving beetle's leg. It turns out that it's quite helpful to generate more extra propulsion and also reduce the water resistance during the recovery stroke. All joints and electronics have been made in forms and modules to efficiently solve the issues of waterproofness and also easy maintaining. For more detailed explanation will be discussed during the interactive section, and you are very welcome to share the ideas. Thank you.
So again, sorry for the last minute change. We had an unexpected change in personnel, so I'm going to present this work. This is mainly the work that David Rawlinson and some of our students have been doing. Over the last year or so, we've been developing this series elastic snake robot. What we're able to do is put a spring in series with the actuator and the output. So it's motor, spring, output. Since we can do this, we can put an encoder at the end of the motor and at our output, and then through Hooke's law, we can infer what is the torque that's going to the system, or at least feel the torque that the system is experiencing. So we have a nice torque control robot now. Here's a video of that robot. I am not doing well with videos today. I promise you, I checked before coming up here again. So here's a video of the robot. Another benefit of this mechanism is that we really iterated on the modularity of the system. What we're able to do now is put the robot together without using any tools. And what's really novel here is not only the mechanical modularity, but it's also the electrical and computer modularity, because now all the modules are able to just plug together, they start talking to each other, and they know where everything is. So you can move one module out, put it someplace else, put another module in its place. It's really full modularity. Here, what we're showing is even though there's a 350 to 1 gear reduction, we can program the robot to experience either no force or some force. We can have it act like it's in honey or have it's in water. So with his own fingers, he wouldn't be able to turn this joint, but since we were able to command it to experience zero force, we can actually bounce it around as if it's, in this case, in the air. And if we wanted, we can have it bounce around again if it's in honey. So one of the things that we did is we implemented a controller. This is from Gil Pratt and his students' work, where we were able to specify that the torque the joint should exert will be proportional to the first derivative of the joint angle. And in doing that, we're able to get the mechanism to sort of feel its way through. This is a form of optical-aided locomotion just by banging.
Hello, my name is Paul Lillebekk. I'm a postdoc researcher at the Norwegian University of Science and Technology. I will present a motion planning framework for snake. The main motivation behind this paper is to enable snake robots to move in challenging environments. This capability will enable numerous applications of these mechanisms. So while previous control approaches for snake robots are based on specifying directly the joint reference angles of the robot, our new approach is rather based on specifying the body shape more or less directly using shape control points and then interpolating between these points to define a continuous body shape curve. This body shape curve is then mapped to the joint reference angles of the robot for the robot by aligning a virtual snake robot along the shape curve and simply retrieving its joint angles. And we believe motion planning based on this shape control point concept will significantly simplify the task of adapting the body shape of a snake robot in a cluttered environment. Here are some simulation examples to illustrate this approach. In this simulation, the shape curve is developed according to sidewinding motion, and the virtual snake robot is progressed continuously forward along the shape curve, and as a result, the physical robot undergoes sidewinding motion. In this simulation, the virtual snake robot is fixed on a shape curve consisting of 3 shape control points, where the end points undergo circular motion, and as a result, the physical robot rolls sideways. This is a vertical wave motion simulation, and here the shape curve is developed according to the shape of a staircase to enable the snake robot to climb stepwise down the stairs. We have also used this motion planning framework to achieve adaptive locomotion in an obstacle environment by assigning spring damper dynamics to the shape control points. So we measure contact forces acting along the body of the robot, and we make these contact forces displace nearby shape control points in order to make the body shape automatically adapt to these contact forces. And this enables the snake robot to maintain propulsion in an obstacle environment without getting stuck. Yes. That's it. Thank you for your attention.
All right, good afternoon, everyone. My name is Philip Walker. I'm going to be talking about our work on human control of robotic swarms with dynamic leaders. This work is done with people like Carnegie Mellon and University of Pittsburgh. So we're all probably fairly familiar with what swarms are, although there are different definitions depending on who you ask. But swarms are typically thought of as robust and scalable systems of multiple robots coordinating through local interactions to give rise to some global behavior. This global behavior is sort of we think of as emergent, and some of the problems with this in terms of human control are that it's difficult to predict what's going to happen with this behavior either before or during the operation. It's difficult to specify this behavior beforehand. It often involves sort of trial and error planning. And so our question that we're trying to address in our lab is what are different ways that we can provide clear, scalable input to a swarm after it has been deployed to help the human influence the swarm to change its goal or change its operation during the mission. So for our approach, we took a leader-based swarm control approach. So we have intermediary leaders that are operating as sort of a way for the human to give the leader commands, and then those leaders can disperse those commands throughout the swarm. Specifically in this instance, we have dynamic leaders, or multiple leaders that are dynamically selected during the mission operation using a modified random competition clustering algorithm. And one of the parameters we can specify is that of an n-hop guarantee, which is a way for us to sort of specify the density of the leaders in the mission. So our hypothesis was that as we raise this n-hop guarantee, that will lower performance, and that we can restrict information to only the leaders and not harm performance. This is just a quick little slide of what the interface looked like. We kept it very simple. Leaders are in red, and the human operator could control the swarm via a virtual joystick. Those commands would be passed to the leaders and then dispersed through the rest of the swarm. So in terms of our results, we did confirm both of our hypotheses. We found that when you move from one hop, when a one-hop guarantee to 2 or 3 hops, that performance will decline, but then going from 2 hops to 3 hops or more, there was really no difference in performance. Part of this is explained by the fact that if you look on the right, there are much fewer leaders in the 2 or 3 hop conditions than the 1 hop condition, but going from 2 to 3, there was really a little difference, a small difference in leaders. And again, there's no difference in terms of restricting information to the leaders, which means humans are just as good at controlling the swarm even when there's limited information.
Hello, I'm Chao Hui, working with Howie. Today I'm going to talk about generating an adaptive sidewinding behavior on a snake robot. Sidewinding is an efficient and fast translational gate, can locomote efficiently on rigid flat ground. To generate sidewinding motion on such a high degree of freedom system, we can use the compound serpenoid curve written on the top of the slide. By tuning these parameters inside, we can change the gate property of sidewinding to let it adapt to different type of environment. Previous research on sidewinding mainly focused on applications for rigid level ground. However, as we start moving towards a more realistic session, for example, for application on this environment is being less structured, we can easily see a pool choice of gate parameters might quickly lead to the failure of sidewinding motion. So the failure mainly comes from two different resources. The first is we do not have an adaptive approach to control the gate parameters. And the second is we have very limited situational awareness, which means the snake does not know what type of environment it is operating in. So this paper is going to focus on these two aspects. So to generate an adaptive sidewinding motion, what we did is an offline learning approach. We use Gaussian process-based expensive optimization. By taking the offline robot experiment data, it can fit a optimal policy, say giving it a slope angle, what the best control parameter should be. Another benefit of the Gaussian process is it not only fits such an optimal policy, it also tells us what the next experiment we should do to maximize our expected improvements. So only after 20 trials of robot experiments, we were able to converge to an optimal policy. So what it does is give it what the current inclination angle the robot is operating on. It will tell you what gate parameters you should choose such that it can maximize the traveling speed of the snake robot. And then to improve the situational awareness, we use an average body frame called virtual chassis, which intuitively represents the orientation of the snake robot in the workspace. And then we use a state estimation technique, which gives us the pose of the average body frame. And then according to a empirically determined relationship between the pitch angle of this virtual chassis and the inclination angle it is operating on, and by consulting the optimal policy, we were able to let the robot adaptively choose gate parameter. Here is one demonstration of the final result, which is the combination of all these techniques combined together.
Hello everyone, my name is Pablo Valdivia Alvarado. I'm a research scientist at SMART and MIT. This work was done in collaboration with Kartik Sekar and Michael Trentafilu. We're presenting a new design for a flapping actuator inspired on fin ray mechanisms found in fish, also called Lepidotrichia. In our lab, we develop under-actuated soft robots for locomotion in fluid environments. And to improve locomotion performance and maneuverability, a very accurate control of body deformation is required. A good example is shown here by these movies in this robot that is mimicking a batoid-type swimming mode. So as a result, we're always looking at new ways of both controlling and actuating body deformation. In this study, we look at fin ray mechanisms found in fish fins. And the basic concept is shown in this figure on the upper left. The model is fairly simple. We have two inextensible rigid beams joined at one end but free at the other. Sandwiched in between the two beams, you have a viscoelastic layer that allows relative motions between the beams in the tangential direction but prevents any separation in the normal direction. As a result, when you force a differential motion in between the two beams at the base, the whole mechanism is forced to bend. So our approach is to try to gain dynamic advantages by combining different material properties. We manufacture a continuum flapper, and the beam regions are made with materials that have modulus that are orders of magnitude larger than the modulus of the intrabeam layer. In turn, the intrabeam layer has a very low shear modulus. Because of the geometry, we can model fairly accurately the formations of this structure by these continuum, relatively simple continuum models. As a result of the low shear modulus, we have a fairly smooth flapping motion. In addition, the intra-array material has a very high normal tear strength, which prevents the two beams from buckling out of plane and separating. So we can control fairly accurately the deflections, the curvature, and the curvature distribution by playing around with the geometry and the material properties. The actuator is also stable at high frequencies. It has a very good bandwidth, and we can model force and energy consumption, among many other things. If you are interested in finding out more details, please look at our sites and stop and talk to me in the interactive session. Thank you.
Hello. This paper is about the design and implementation of a low-cost, pump-based depth control of a small robotic fish. I am Aliprandis Ioannis, and this is work done along with Makrodimitris Michalis and Papadopoulos Evangelos at Control Systems Laboratory and UA Athens. We're interested in controlling the depth of small underwater vehicles. Our goal was to develop a methodology for controlling the depth of small underwater vehicles at minimum cost and size. In the past, people have done control using on-off control or fuzzy logic control. They used bulky and expensive depth sensors. They didn't handle nonlinearities such as dead zones, actuator saturation, etc. And most importantly, they could not control depth at zero speed because they were using fins. In our work, we developed the first methodology for controlling the depth of small underwater vehicles with a small DC pump, a pump encoder, and a pressure sensor. We verified it by simulation and experiment. We used partial state feedback control with nonlinearity inversion. The gain tuning was implemented with root locus and simulation. We implemented it with components of low quality and cost. And we simulated and tested experimentally the pump dead zone, the actuator saturation, the depth sensor noise, and the disturbances due to leakages. At zero speed, we achieved depth control with good accuracy. Here on the left, up, you can see the actual robotic fish. Down is the concept we implemented. And on the right, you can see the results. The red line is the simulation of the ideal model. The black line is the simulation of the real model, and the blue line are the experimental results. Thank you very much.
Well, to save some time, my name is André Dietrich, and I'm a researcher at the University of Magdeburg at the Department of Distributed and Embedded Systems. Just wait for the topic. And the work I'm going to present is dealing with the problems of data residing in smart environments and how it can be structured and organized in a way that any kind of valuable information can be generated out of it. So to start with, a systems point of view, well, data might look like this. Just think of a robotic or mobile robotic platform, for example, that for the first time enters a manufacturing hall. It might require a map of the environment or of the target environment, some sensor measurements that have been done in there, or probably also some information about additional systems in that area. Well, at this stage, the data is somehow, it's there, but it's simply not organized, not really accessible and distributed on different nodes in the system. And so what we did at first, starting bottom up, we tried to categorize data according to metadata, which can be used to describe systems like robots, sensors in terms of their capabilities, interfaces, and also data formats. Then we have abstract data, like maps abstracted from a set of laser scans, recognized objects with their geometries, humans, and so on. And of course, a whole bunch of measurement data with status information commands which have both a real-time as well as an historical value. And on top of this, we put in virtual overlay database by using cloud-based techniques. And the idea was that every node in this structure now represents a certain entity of the environment, which might be some kind of a location, a robot, a sensor, and so on. By using this structure, which can be for simplicity described as a distributed scene graph, it's possible to reconstruct something like this, a local environment model, which of course has to be connected to the real-time data to keep up to date. We believe that this kind of environmental representation can be used as an application-specific or central representation from which all other representations as well as informations can be derived of. And for this purpose, we have developed a new kind of declarative language called SelectScript as a general interface. So, well, it looks somehow like SQL, and you can use it like this. Simply select everything from the environment and generate an occupancy grid map out of it, if you want to. Or if you are interested in all identifiers and positions of objects that are unreachable distance to a katana manipulator. Or if you want to do some kind of increased localization, for example, by using external sensor measurements, you can query for all sensors, in this case, that are measuring a certain entity. Or simply another representation. So, but it's even possible to define it.
Hello, my name is Tobias Nageli. Today I'm going to talk about our work on environment-independent formation flight for micro-aerial vehicles. This work was done at ETH Zurich. We took inspiration from nature. This video shows a large swarm of starlings which is in a Wasem site. In particular, you can get an impression of how highly dynamic and accurate such a formation flight can be. Such formations have high potential, as for example in entertainment and search and rescue. Formations like this have inspired recent work in robotics, as for example path planning for terrestrial robots. In particular, flying formations with MAVs has been studied by various groups. Here we see one example of MAV formation flight by UPenn. This formation flight is controlled by a centralized computer, and a room-fixed Viken system gives highly accurate and fast position data. On the right side, we see an outdoor formation that relies on a GPS system and again, centralized control. Central control and external tracking can be major hurdles for deployment. In our work, we want to enable accurate formation flight indoors and outdoors in arbitrary environments. This means we can't rely on external sensors such as GPS or a room-fixed Viken system for formation stabilization. We don't want to rely on external infrastructure to stabilize the formation. Therefore, our approach only uses onboard sensing using vision and inertial measurements, as well as an agent-to-agent communication framework. We estimate the formation state using a distributed estimation and control strategy. On a high level, our algorithm works like this. The distributed estimator and controller consists of individual instances running on every agent of the formation. One specific problem we had to solve is to estimate the formation state. The state of the formation is estimated using a distributed extended Kalman filter. The recursive filter equation contains a prediction term as well as a measurement and communication term. This video shows our proof of concept system flying indoors. Here only the center of gravity is steered with a remote control, whereas the algorithm stabilizes the formation. The agents can also perform dynamic formation changes. We also tested our system in an outdoor environment. To our knowledge, this is the first implementation of a flying formation relying on a completely distributed control and estimation architecture using onboard cameras only. Thank you very much. I'm looking forward to talk to you during the interactive session.
Good afternoon, my name is Stefano Carpin, and I will present a paper about rapid multivariable deployment with time constraints. This is joint work with Marco Pavone at Stanford and Brian Sedler at the Armored Research Lab, and is part of the MAST CTA. The problem we are considering is the following. We're given an environment within which n locations have been identified, And we have given K robots with K much larger than N. And the objective is to compute a control policy that will bring at least one robot in each of the locations so that the robot can collect information to pass it later on to human operators entering the environment. And this task has to be completed obeying to a strict temporal deadline. And we want to compute the exact probability of success or failure. The task will be executed over robots like the micro-aerial vehicle you see down there. So we achieve robustness through redundancy, because it's okay to break some of these robots along the way. And there's obviously a risk-velocity trade-off. The faster you move to make the temporal deadline, the more likely you are to break things. So we solve this problem as an instance of chance-constrained decision-making, and in particular, we use constrained Markov decision processes. For those of you that are familiar with Markov decision processes, CMDPs extend the model by introducing D, L additional costs, lowercase di's, and L bounds, capital case di's. And each of these costs is a function of the state and the action, like the primary costs. So solving a CMDP means finding a policy that minimizes the primary objective function while making sure that all the additional costs are bounded. Despite the similarity with Markov decision processes, the solution is rather different. You cannot use dynamic programming. You have to use this linear program that you see on the right. And most importantly, the optimal policy may turn out to be randomized. So we solve the problem as follows. We start with a graph. Every vertex of the graph is mapped into a state, into the CMDP. We add an additional state, which is called S, the one you see down there on the right, which represents failure. And for every edge in the original graph, we create a set of actions in the CMDP, relating time to make a move with probability of failure. If we use this model, we get to the main theoretical result, which is that we can exactly compute the failure probability for a single robot. And this in turn maps to the failure probability of the team as a whole while trying to complete the deployment task. Eventually, this leads to these charts that we call analysis and design plots, which relate quantities like the number of robots, the time threshold, and the probability of success, so that you can answer questions like how many robots do I need to complete a task within a certain temporal deadline with a given level of confidence. And there are many more details. If you're interested, you can come to poster number 14 later on. Thank you very much.
Hello, everyone. I am Hyungju Park, a graduate student from University of Illinois, who's working with S. Hutchinson. The title of this study is A Distributed Optimal Strategy for Rendezvous of Multi-Robots with Random Node Failures. In this study, we propose a distributed motion control algorithm for a group of multiple robots with limited sensing that achieve rendezvous tasks in the presence of random node failures. So in this study, we consider a particular case when the connectivity between pairwise nodes is determined by the Euclidean distance between them. So we consider a distributed discrete time synchronous system, and at every time step, each node obtain their control by solving an optimization problem, and we call that problem a distributed rendezvous problem. And if we model the random node failures as random variable, we construct a stochastic version of that and obtain the solution with SQP. So here's how the distributed rendezvous problem looks like. And so for the fault-free case, each node basically moves to the average of the position of the neighbors and the position of the node itself. And by modeling in the case of faults, we minimize the expectation of the cost with respect to the probability of no failures. And here's some examples of our simulation results. We compared our result with a circumcenter algorithm. So in the video, on the left videos are for a circumcenter algorithm, and the right are stochastic version of our algorithm. And the top is when there are no failures, and then bottom when 10% of the node fails. As you can see, our algorithm shows approximate convergence in both cases. And we conducted this simulation with 100 samples and verified that our algorithm works statistically better than the circumstantial algorithm. For those of you who have questions or interested in more details of it, you can visit me during the interactive sessions. Thank you very much.
Good afternoon. I'm Seung-Kyu Lee from Rice University. Let me give you a talk about cohesive configuration control for multi-robot system. So the purpose of our controller is to deform this kind of initial configuration that contains a concave boundary and even more bottle-like shape to the finite configuration that is fully convex and regular shape finite configuration. Our algorithm is based on the previous work by Dr. Reza Ulfari-Saber at Boston University, but his flocking controller has few drawbacks such as allowing some disconnected robots, voice, or an articulation point. To solve this algorithm, we propose a boundary force algorithm which is inspired by a nature of sufficient tension force on a water drop. So every robot basically detects and updates whether it is on the boundary or not. And every boundary robot pairs generate an attractive force and compute the vector sum, which is called boundary force. This boundary force removes all concave region and makes some additional inward pressure to make finite configuration more cohesive. So here is some simulations. Okay, let me keep going. So unfortunately, some initial configuration has some articulation point that might be some failure even we use our boundary force algorithm. To solve this problem, we also propose on network sensing and mode switching algorithm. So first, if some robot detects an articulation point, then all robots switch to another mode called parent following. And if all articulation points are removed, then all robots switch back to their normal flocking mode. So this is our simulation result using 104 robots with several articulation points in it. And our result shows that with our given network sensing algorithm, all robots completely form the target configurations. And here is our experimental result showing our algorithm. They are all implementable.
Hello, everyone. My name is Adam Victor, and I'll be presenting our paper on decentralized and complete multi-robot motion planning in confined spaces. So our project deals with the problem of coordinating the motion of multiple robots in single-lane tunnel environments. So that's basically any environment where it's too narrow for two robots to pass one another. As this scales up to larger problems, it's really challenging to handle this with a centralized control architecture where one computer is planning the motion of all the robots. Additionally, these confined environments often have limitations on communication. And so a decentralized control architecture is often the best way to get around these two constraints. We propose the push-swap-wait algorithm, which is the first algorithm to be both decentralized and complete, meaning that it guarantees a solution will be found in all cases. In order to make that guarantee, we have to make a few assumptions. Most importantly, we assume that there are fewer robots than there are leaf nodes. We also assume that the robots can form ad hoc communication networks and that they have knowledge of the map beforehand. So jumping into a little bit of how the algorithm works, we start by building a spanning tree of the environment using a breadth-first search. We then assign a unique priority number to each robot using a post-order traversal of the tree. The highest priority robot gets to move first, so it drives towards its goal and pushes all the other robots out of the way as it goes. In many cases, it isn't going to be able to just drive straight to its goal, and it'll have to swap with one other robot as needed. We also added a waiting mode to the system in order to guarantee completeness, even in cases when communication is lost and robots leave the network. We provide a proof of completeness in the paper. It's a bit lengthy, but to summarize it here, we start by proving that any two individual robots can swap, and that once they've swapped, they'll never need to swap again. Then we can show that the highest priority robot is solved through a series of these swaps, and that once it's solved, it never becomes unsolved. So then by iterating through all the robots, beginning with the highest priority robot, you can show that the algorithm as a whole is complete. We tested the algorithm in MATLAB, running over 200 random problems, as well as many that we designed specifically to stress aspects of the algorithm. We also implemented the algorithm on the Dr. Robot Jaguar platform and had systems of up to 4 robots successfully navigating a hallway. To summarize our results, the runtime is linear for this problem, and it scales very well to large systems, so we think it's very well suited to real-world applications. Thank you, and I look forward to talking to you more in the interactive session.
Hi, my name is Linh Nguyen. I come from University of Technology, Sydney, Australia, where I have done some research regarding robotic sensor network that can be used to monitor spatial phenomena such as temperature, humidity, and rainfall. In this study, we utilize mobile sensor network for efficient spatial prediction. As you know, in environmental study, it's necessary to monitor environment. However, the fundamental question is where we can deploy a sensor to monitor and predict the field efficiently. Suppose that if you deploy sensor permanently, the network cannot adapt the change of environment or cannot respond to a failure of a sensor. Therefore, we propose to use a mobile robotic sensor network to collect measurement by moving on optimal sampling paths. The disadvantage of mobile sensor network is resource constraints, such as communication, energy, or memory. The challenging in this issue is how mobile sensor network can collect maximum information with efficient computation. In extinguished work, is frequently used Gaussian process to model spatial field. By measurement collected, we can predict the field at an observed location by using Gaussian process regression. However, factorizing covariance matrix is cubic in dimension, which makes computation very complex. In this study, we propose to replace Gaussian process by Gaussian Markov random field, that's featured by Markov property. With the sparse precision matrix, Gaussian Markov random field very significant benefits in computation. We also propose information criteria for finding sampling paths to minimize uncertainty as on unpredicted location. In result, we compare our method with a public approach and a standard Gaussian process. And as you can see, a root mean square error result shows that our approach very highly comparable to standard Gaussian process. And in computation time, our approach very appealing. We would love to discuss further this issue in interactive session with you. Thank you very much.
We're looking at a sparse sensor network where the sensors want to share information with each other but cannot communicate directly. Unmanned aircraft are perfect to act as mobile routers or data ferries and enable delay-tolerant communication in this sensor network. The throughput of the network depends on the communication link scheduling between the sensor and the unmanned aircraft and the motion of the aircraft around the environment. Of course, to optimize these parameters, we need accurate models of the RF environment. Traditional parametric RF modeling techniques struggle in complicated environments because of shadowing, multipath, or unknown noise sources. Planning a ferry trajectory with such a model will result in worse network throughput than expected and is far from what can actually be achieved. Thus, for accurate planning and optimal performance, some form of online learning or refinement is necessary. Typically, online learning plans trajectories to maximize the learning, but we're primarily interested in data ferrying. Therefore, this paper focuses on integrating the non-parametric learning with the optimal path planning for data ferrying by doing the learning opportunistically using the communication that's already happening between the sensor and the aircraft. Starting from some prior RF model, the data ferrying problem is solved in a cascaded manner. A genetic algorithm with heading control generates a good trajectory, and a fast near optimal policy generates the bandwidth allocation for each trajectory. The aircraft then flies the selected optimal path, ferries the data, and samples the environment. By comparing the ferry's measurements with that a priori RF model, a Gaussian process can learn the RF variations in the environment. That is, it can learn the errors in that a priori estimate. The predictions of the Gaussian process are used to update the radio model, which the ferry planner uses in the next iteration. Our simulation study shows that through this iterative process, the ferry performance grows rapidly, achieving 80% of optimal within 4 iterations and 93% after 9 iterations. Our recent results show that compared to least squares estimators like the ones shown in green and red, Gaussian process learners shown in blue consistently perform better in environments with diverse characteristics and complexities. So please come see me at the interactive session to hear more of the details and the results. Thank you.
Good afternoon, everybody. My name is Rajdeep Dutta. I'm from University of Texas, San Antonio. Today, I'll be talking on a novel formation controller, which not only makes a formation of multiple UAVs around a target, but also maintains the connectivity of the network. Connectivity of a network plays a very crucial role, and without it, one agent or multiple agents may get lost being out of communication. So here I show a sample video of how connectivity may fall down to 0 and the network may not work, the formation may not work. So in this sample video, 4 UAVs are trying to track one target, and they are starting from a particular position, and they want to make a desired diamond-shaped formation, which is shown in the right figure. But as you can see, because the connectivity is going down to 0, so after a certain time, 2 of the agents, blue and red, they go out of the communication. So in order to overcome this drawback, we consider a time-varying topology, and this topology can be captured by a time-varying Laplacian matrix, where the matrix elements are decreasing function in relative distance. So this matrix is positive semi-definite matrix, and the matrix's second smallest eigenvalue gives us a measure of the network connectivity. So we want this second eigenvalue always greater than 0 in order to maintain the connectivity of the network. So here is the nonlinear based backstepping technique based designed controller, which tries to drive the relative distance vector towards the desired one, and we artificially make the new controller weights Wij so that these weights are actually considering the connectivity case. These weights are made in a way that whenever the connectivity goes down, this reinforces the connectivity. Because this Wij has a opposite profile of the Laplacian elements Aij, so that's why it actually increases with distance. So now I show a typical simulation results where the top figures correspond to the existing controller and the down figures correspond to the new controller. So the right side of the figure shows the connectivity profiles. As we can see, the new controller is able to make the connectivity. And here is a video. It's a
My name is Alessandro Giusti. I am presenting this joint work with Fabrizio Ghiringhelli, who is with Politecnico di Milano, and other co-authors at my institution, which is the Dalle Molle Institute for Artificial Intelligence in Lugano, Switzerland. So when you develop and deploy a multi-robot system, you look at your robots moving around, and at some point maybe you observe something that is not quite right, and you need to make sense of what's happening. Maybe sensing is not working, or there is some issues with algorithms or actuation. Then this is already a challenge to solve when working with one single robot, and becomes a nightmare when it involves multiple interacting mobile robots. So our goal is to help the system designer make sense of what happens in a multi-robot system. We visualize an augmented reality overlay to the physical environment, which shows the spatially located entities that a robot is perceiving or that are part of the robot's internal state. Here we show the view for robot 14, and the circles represent the perceived positions of the neighbors. Our solution has two components. The first is a visual tracking module, which detects, identifies, and tracks robots by means of a single coded blinking LED per robot. It also integrates odometer information, which is sent by the robots in order to track through occlusions. Moreover, this also allows us to keep track of the robot's orientation when the robot is stationary. The second module is an augmented reality overlay, which receives data from robots. In this case, it is visualizing debug messages next to the robot that originated them. Robots can also visualize spatially situated data expressed in their own reference frame. For example, this is their view of the world from robot 15. The square represents the perceived position of the yellow navigation landmark. The system is interactive and allows us to change the subject robot by clicking on it. For example, now the view has switched to robot 32. The system works in real time and only requires a fixed camera, plus one blinking LED per robot. We are ready to release our implementation. Please contact us if you are interested. Thank you.